Population genetics is the study of inherited variation within and between populations over time and space. An important part of population genetics is the Hardy-Weinberg Law. This states that allele and genotypic frequencies will arrive at and remain at equilibrium frequencies after one generation of random mating if all assumptions are met. At equilibrium, the genotypic frequencies are p squared plus 2pq plus q squared, where p and q are the frequencies of the big A and little a alleles. The assumptions of the Hardy-Weinberg Law is that there's an infinitely large population, random mating, no selection, no migration, and no mutation. To demonstrate the Hardy-Weinberg Law, we're going to look at a population of lions and their fur coat. In total, there are 200 lions that will be in the population. However, I'm just going to demonstrate 3 of them to show the genotypes and phenotypes that we will be looking into. The dominant would be an orange fur coat, which would be represented by big O, or heterozygous O, and the recessive is a red fur coat, which is represented by little o, little o. In our population of lions, we found that 48 lions had homozygous dominant alleles with an orange coat, 96 lions had heterozygous alleles with an orange coat, and 56 lions had recessive homozygous alleles with a red coat. In order to find the frequency of the alleles and genotypes in the initial population, I have demonstrated below how to do it with the Hardy-Weinberg equation p squared plus 2pq plus q squared, where p and q are found from the frequency of the single alleles. I will also show a cross between 2 heterozygous lions that show that the initial Hardy-Weinberg equilibrium values remain after a generation of mating. This proves the Hardy-Weinberg assumptions were all met in the population. Now, if a population were to experience selection, this would violate one of the Hardy-Weinberg assumptions and not produce the equilibrium values we saw earlier. Selection can either be directional, disruptive, or stabilizing. In order to demonstrate the effect selection has on the original population, we have to assign a fitness. That will reveal the survivors of the population depending upon their genes and alleles. As you can see, I have created a fitness for the original population, which determines the survivors after selection. The genotypic frequencies after selection are then calculated and compared to the original ones we determined before. This allows us to categorize this as directional selection. We determine this as directional selection due to the increase in orange genotypes and the decrease in red genotypes. This type of selection is probable for the population due to the orange lions being able to match their environment better. This will help them with catching prey and avoiding predators, while the red lions are unable to do so. Over time, this will ultimately seek to make all the lions have a homozygous dominant allele for orange fur.